welcome back. Section 206, we get to play with a numerical method. And there's whole courses on numerical analysis. This just kind of gives us a little taste of it. You've had a little bit of work with that before in your Calc 1 class when you looked at the bisection method and Newton's method. So you've seen a little bit of this before. This is sort of the differential equations version of some of the work that you did back there in your Calc 1 days. So suppose we know that dy dx is some function in x and y. And they give us an initial condition of x naught, y naught. And what we want is an estimate of a y value or a hopefully nearby x value. So 2.1, I just kind of asked you to read through that. We had those very pretty vector fields, and we'll just kind of walk you through a little bit of it now. That's way bigger than we'll need. So the idea with a vector field is that we have this thing and we just input an x and a y and find out what the slope would be at that point, and we draw a little tiny arrow to indicate that slope. And they make very beautiful graphs, very pretty to work with. Unfortunately, they're extremely time consuming as far as actually working with them. Oh, this is plenty. That's more than enough. All right, again, I'm just kind of roughing these in. We'll use our imagination and pretend that all these are nice and neat and evenly spaced. So we're somewhere in the xy plane, and here's a bunch of ordered pairs. So let's say that we have this differential equation, and we know one initial value. So this one will be our x naught, y naught. And let's say that my end goal is whatever x value this is. So what I can do is basically follow the arrow. So let's say, for the sake of argument, we plugged in this x, this y into f of xy and found it had a slope of, well, let's say 1. So then I'd follow the path to here, and let's say this guy had a slope of 0. So then I follow him to here. This guy had a slope of, let's say, positive 2. So I go up to, there's where we land next, and then we go, let's say down 1. All of these arrows we're assuming we're already here. So then here is my output value, and I have my x value that they gave me as the goal, and this was the desired y value. This is the prize we're after. So the idea is that we basically sort of trace our route following the derivatives, and there would be lots of other arrows leading us other places. So maybe they got steeper on each case, so less steep going this way. And we would have a different end result if we started with a different initial condition. We would follow this path down, or we would follow this path further up. But just this was the path we sort of traced out. So I want to kind of focus in on just what's happening between this x naught, y naught, and our first point. So let the increment of x be h. So h is some arbitrary positive constant. This is how much we're changing by in the x-axis each time. A little imagination, and those are all spaced nice and evenly 8 units apart. So this point was x naught, y naught, and we followed its slope to get to x1, y1. So I'll do a little zoom in of that. So here, this is a line with slope f of x naught, y naught. And we got to point x sub 1, y sub 1. Well, we know that the slope is change in y over change in x. If our change in x is said to be h, x1 could also be expressed then as x naught plus h. So then I can say f of x naught, y naught is y1 minus y naught over x naught plus h minus x naught. So notice the x naughts are going to bail on us. And in fact, let's just clear the fraction then. H times our slope, which we find by plugging in x naught, y naught, is the change in y. If I want y1 by itself, just add y naught to both sides. So then y1 is y naught plus h times f of x naught, y naught. Now there's nothing special about that point, that those 2 points that I picked out, so we could generalize that. And I'll do so on the next page here to say y sub n plus 1 is y sub n, so the previous y, plus h times our derivative at the previous spot, x sub n, y sub n. So this is a good way to approximate solutions. So let's do an example with this. dy dx is going to be x minus y, and they gave us initial conditions that y of 0 is worth 4. Now this one is actually solvable, so we can not only get our estimates, but we can actually see the actual values as well and find things like the absolute error and the what they call percentage relative error, just what are we off by. Ones that are not solvable, obviously, we can only do bounds on the error. We wouldn't be able to find the actual error. But as long as this one is solvable, let's just solve this one real quick. So dy dx plus y is worth x. Integrating factor e to the integral of 1 dx is e to the x. So we have e to the x dy dx plus e to the x times y is worth x e to the x. So left side is now e to the xy with the derivative taken. So we recognize that as just a product rule derivative of y times, keep the e to the x, differentiate e to the x, you still get e to the x, keep the y, equals x e to the x. So integrate both sides. So then we have e to the x times y is worth, so u here is x, dv is dx, du is dx, dv would be e to the x times dx, v would be e to the x. So u times v, x e to the x, minus integral of v times du, e to the x times dx. So e to the x y times y is x e to the times e to the x minus e to the x plus arbitrary constant c. And we do have an initial condition there, so when x is 0, y is 4. So e to the 0 by 4 is worth 0 times, doesn't matter what at that point, minus e to the 0 plus c. So that term's gone. 1 by 4 is 4. 4 is negative 1 plus c, so c is 5. So this one was solvable. We know that we would end up with either e to the x times y is worth x e to the x minus e to the x plus 5, or a simpler version, y is x minus 1 plus 5 e to the minus x. Okay, so we have, this is our real answer. This is how we get our estimations. So I'm going to grab just those two pieces of the puzzle. We'll bring those guys along. So dy dx we know is x minus y. And we know that our real solution was y equals x minus 1 plus 5 e to the minus x. So n is just the number of iterations we've done, so no iterations into it. They did give us an initial condition of what was it, 0 for the x and 4 for the y. For this one, we're going to let h equal 1/10. So then our first iteration, 0 plus 1/10 is 1/10. And for y sub 1 then equals y sub 0 plus h times our derivative. So y sub 1 then is 3.6. Our next iteration, now I'm using the 3.6, the previous y value, plus h value times our x minus y, so 0.1 minus 3.6. So that one will spit out 3 1/4. So we went up to 2/10, we got 3 25/100. So we keep repeating that process. So then here, I'll leave a little bit of room there. Y sub 3, so we use y sub 2, so 3 25/100 plus 1/10 of the slope. So our slope this time 2/10 minus 3 25/100. So we plug and chug on that guy, and that will give us 2 945 thousandths. So y sub 4, 2 945 thousandths plus 1/10 of 3/10 minus 2 945 thousandths. So then that one is our y4, so 0.4 for the x value, and y sub 4 landed us at 2 6,805 thousandths. So y sub 5, we take that value plus 1/10 of the previous x minus previous y. So if my goal was to get to finding y of 0.5, here is my reasonable estimate of that, 2.45, 2, and then we have another 4, 5, so we'll round that 4 up to a 5. So you might have noticed I left a lot of blank space there. One thing we can find is the actual. So y actual is just plugging these x values into the real solution, since this one was solvable. So if I plug in 0, I get 0 minus 1 plus 5e to the 0. They get the same 4 spit out there. So our error between absolute error between the actual and the predicted was 0. So the percent relative error would be absolute error out of the actual and then times 100, which in this case is 0. It gets more interesting on the other lines though. So if I plug in 1/10 into this, I'm going to round this just out 4 places. So I get 3 and 6,242 10,000ths. So then I find the difference, absolute difference between those is the 242 10,000ths. So then our percent relative error, absolute error out of the actual value, and then times 100 to just slide that decimal over. So then we have 0.6677. So still under a 1% error. 2/10, then we just have a 2/10 plugged in for x. We get our y value out of the calculator. 3.2937 is out to 4 decimal places. So our absolute error, we just find the difference between the actual and the predicted value, and we don't care about sign. That's why we're saying absolute error. So then 0.0437, and then our percent relative error, this over this, and slide the decimal 2 spots. Error over actual and times 100. So we get 1.3268, so about 1 1/3% error on that one. And then as we get further out from our initial point, the error is going to get larger. So we have, let's see, 3.0041 for an error of 0.0591, and a percent relative error, we're at 1.9673. Plugging in the 4/10 into the actual formula, we get 2.7516 approximately. Obviously not exact since we have a transcendental number there. Our error 0.0711, absolute or percent relative error 2.5840, and finally the real value at x equals 5/10 if we have the initial condition of 0.4. It's predicted to be 2.5327, and our absolute error then 0.0802 for 3.1666. So we have a little over a 3% error in that. So what are some ways to cut down on the error? One is to make sure you're making predictions close to your initial conditions. 2, we can actually decrease the distance we jump between the x values. That should give us a better estimate. So this one I did sort of by hand with the calculator, like we're going to have to. The next one I just figured out how to play around with Excel and get us there. And playing around with Excel and getting us there, I let h equal, for my Excel one, 0.01. So instead of jumping by 1/10 of a unit each time, I jump by 100th of a unit each time. So instead of using 5 rows past the 0, I needed 50 rows past the 0 to get to the 0.5. But that 50th row, n was 50, x sub n was the desired 0.5, and the y sub n, the predicted, was 2.5250. Y actual, same as before, the 2.5327. So our absolute error, 0.007, and I think it rounded it down to a 6, since we had digits beyond what you see here. So sometimes that will be off by just a hair. So then our percent relative error, which again is absolute error divided by y actual, and then slide the decimal 2 spots. That time it was 0.3010. So we went from a 3% error to just barely over 0.3% error. So you can either take smaller steps and make more rows, and Excel is great for making more rows of stuff, or you can, again, if you have an initial condition very close to the value you're wondering about, the error should be relatively small. All right, so in 2.6, I would try out 1 through 4. All the rest of them require software, and I don't know what kind of computer each of you have at home and how to get everyone access to the software. And frankly, the technology changes very quickly anyway. So you can kind of read up on it. If you have a computer to play around with some of the other stuff, go for it. But 1 through 4 is stuff that I know everyone can do with the equipment they have at home. And as you saw, these are long enough problems as it is anyway. On number 3 and 4, the h equals 1/10 would be sufficient. They also ask you to do the 5/10. I don't think beyond comparing the 1/10 and 5/10 once in Excel, as we did here, you're going to learn anything more than smaller steps would give you a more accurate result. And these tables take quite a while to make by hand, even for the relatively larger step sizes. So h equals 1/10 should be sufficient. If you do want to try the h equals 0.05 and you have Excel at home, just try that if you have Excel. All right, so if you have questions, please get in touch. Otherwise, I will see you next time.